Welcome back to another module of this course, Microwave Integrated Circuits. In the previous module, we had talked about broadband impedance matching and how quarter wave transformers are used for obtaining a certain bandwidth of impedance matching. But then we also saw that quarter wave transformers cannot provide a very high bandwidth. They have their own limitations of bandwidth. And one of the ways that I suggested in the previous module to increase the bandwidth could be to have multiple sections of transmission lines cascaded to each other. So let us see how to do that. The first problem that we have with multi-section transformers is, if we can draw those multi-section, suppose we have two sections of transmission line, one having characteristic impedance Z1, the other having characteristic impedance Z2, connected with each other in cascade, and suppose V1, okay, so this is junction 1, junction 2. Now, if we, and suppose say gamma in is the input reflection coefficient before the first section, or no, sorry, it's here before the first section. This is where gamma in is. And now the first problem is that if suppose there is an incident wave A1 entering the first section, then it will be reflected from this junction. Some of the incident wave will be reflected from this junction and say produce a wave B1, and some of them will continue to the second junction, say that is A2, and after reflection that will be B2. Now, had it been till this point only, we wouldn't have any problem. Problem arises, if we can go back to the circuit once again. The problem arises that this reflected wave B2 will also, there is a possibility that this B2 will also be reflected back again, and here lies the problem. Now, this reflected wave will be further reflected wave and so on, and that will be an endless process, and it becomes really complicated, as we shall see. Now, instead of that, if we could, if there was some kind of possibility by which, say every incident wave undergoes only a one level of reflection, that is, it is reflected either at this junction or at this junction. There is no multiple reflection happening. Then our expression for this input reflection coefficient becomes much easier. See, the problem here is to find out this expression for input reflection coefficient. If we could have a simple expression for gamma in, then it would be more easier to design sections. Of course, if you want a very rigorous analysis, then you have to have a proper, well-defined closed form solutions for gamma in. But if there are certain conditions when we can neglect the second level reflections, then perhaps, as we shall see, we can obtain a simple expression for gamma in. Now, the condition which allows this to do so is the case when Z1 and Z2 are very close to each other. The closer they are, the lesser will be this second level of reflection. So, if we can go back to our figure, let me draw a fresh figure. So, we have one transmission line with characteristic impedance Z1 and another with characteristic impedance Z2, V2 plus is the incident wave at junction 2, and V2 minus is the reflected wave at junction 2. V1 plus is the incident wave at junction 1, V1 minus is the reflected wave. Now, if we consider this point to be 0, and so then for a reference system where our coordinate origin is at this point, then this junction 2 will be plus L, and for an origin system where this is the origin point, junction 2 is the origin point, for that system this junction 1 will be minus L. Okay, so then we know that V1 of 0 in this coordinate system where junction 1 is the origin, that will be equal to V1 plus V1 minus, and that in terms of the V2 plus can be given by and I10, which we saw is the difference. This can be given as like this. So then I hope this is visible. So I1 of 0 is I2 of minus L with appropriate coordinate transformations, and then gamma in so gamma in which is defined as V1 minus upon V1 plus, that with this definition we can write 1 plus gamma in is equal to V2 plus upon V1 plus So this is the two expressions that we can find for 1 plus gamma in and 1 minus gamma in. And if we then take the ratio of these two expressions, that comes out to 1 minus gamma in upon 1 plus gamma in is equal to Z1 upon Z2 is whole upon and solving for gamma in gives this expression, where gamma 21 is equal to this expression. Now, this is of course the complete expression for gamma in with no assumption about what the values of gamma 2 of Z2 and Z1 are. For any values of Z1 and Z2, we will get the same expression. And of course, this expression is only when there are two sections. Now, if we suppose have a third section, then we have to again do the same process. We have to repeat this same process for the third section, and the more the number of sections beyond 2, this expression will become more and more complicated. If you, as I said before, if you want a rigorous solution, then of course you have to solve it completely. But suppose you have that mismatch between Z2 and Z1 as small, then we can think of a different solution actually. The solution is that this quantity gamma 21, which is dependent on the difference between Z2 and Z1. If suppose Z2 and Z1 are not that different, Z2 is very close to Z1, then gamma in can approximately be written as like this. What happens is when Z2 is very close to Z1, then this gamma 21 is small, and so this expression gamma L and gamma 21 magnitude will be even smaller, because gamma L is either 1 or lesser than it. So then in that case, if this expression holds true, then we can simplify this expression to this form. Now, what is the significance of this expression? This is of course a simplified sum of two quantities, but if we just want to see the physical significance of this expression, then we can go back to our circuit. Now, what it means is that gamma in is the sum of two reflections. One is the reflection that is taken place at this junction, which is accounted for this term, and the other is the mismatch that is happening at this junction. Now, this expression is well known. We saw that the reflection coefficient is phase shifted twice the amount of phase shift provided by a transmission line, and so that comes from theory. And gamma 21 is simply the mismatch factor between this Z1, this transmission line having characteristic impedance Z1, and this transmission line having characteristic impedance Z2. Note that if Z1 is equal to Z2, then gamma in is equal to gamma L minus J to beta L, which is the expression we know very well. So, the reason we can do this is because we are only considering a single level reflection, which means that one reflection is happening due to the mismatch between Z1 and Z2, and the other reflection at the load end. So, by making this simplification, we are not considering the second level reflections that might happen here, that is the reflected wave being re-reflected at junction 1. So, that is the simplification we are making, and we are saying that that is valid because the mismatch between Z1 and Z2 is very small. Now that we have this simple expression, this makes it much easier to derive the condition when we have not two sections cascaded as like this, but then n sections cascaded with each other. Let us see what happens when n sections are cascaded. So these are n sections of transmission lines cascaded to each other. This is the input section, Zn is the last section and RL is the load. Gamma ins are the reflection coefficients at the junctions of the various sections. Now here we assume that all the sections have identical electrical lengths, and that is given by beta 1 L1 is equal to beta 2 L2 is equal to beta 3 L3, and that is equal to some value theta. Now if we apply the formula we just discussed in the previous section to each section now, so say we are considering, we want to find out the input reflection coefficient, and that input reflection coefficient is equal to gamma in 0 theta, which is equal to gamma 1 0 plus gamma in 1 minus j 2 theta. So this is the expression. So this is like gamma in 1, which is the reflection coefficient at this point, multiplied the total by e raised to minus j 2 theta, where theta is the electrical length of this section and the electrical length of all the sections. And gamma 1 0 is the mismatch between this beginning section Z0 and Z1. So gamma 1 0 will be equal to Z1 minus Z0 upon Z1 plus Z0, and then so we have this expression. Now gamma in 1 itself can be further expanded, so we have gamma 1 0 plus gamma 2 1 raised to minus j 2 theta plus gamma in 2 raised to j 4 theta. So this is our, this expression I have obtained by expanding gamma in following the same formula, and I now get this further expression. And then if I expand it further, if I expand now gamma into further according to the same formula, I get this equal to so I can continue like this for all n sections. Every time, the only difference will be that every time this power, this exponent of this E will keep on increasing. So then for n sections, I can write this general formula where these gamma 1 0 terms are these gamma mn terms are given like this. or simply I can write it in a summation format. So, this is the formula finally we obtain. Here we have simply instead of writing this as gamma k plus 1 comma k, I replace this with k, that is the mismatch expression is replaced like this, just for convenience, as we shall see later on. So, this is the general formula for the input reflection coefficient when we have n sections connected in cascade. Let us see what are the implications of this expression. So, if we can go back to the our slide here, first thing that we see that this is of the expression of a Fourier series. This has the same expression as a Fourier series. So, this is a Fourier series, and that is true because theta, as you see, this theta is this gamma k, which is a function of theta, itself is in periodic in with gamma k replacing itself after every increment of theta by pi. Now, the second conclusion that we can draw from this expression is that the center frequency will be at theta equal to pi upon 2, and at theta equal to 0, which corresponds to f equal to 0, that is dc, at dc we should have gamma in theta equal to RL minus Z0 upon RL plus Z0. This is because as we know, even if we have n sections, if we go back to the previous slide, now if at DC from the input to the output it will be one shorted line. So, the input reflection coefficient at DC will simply be RL minus Z0 upon RL plus Z0. That is why I have written here that at DC gamma in theta should be this simple expression. This must be satisfied, otherwise if this is not satisfied, then there is something wrong with our theory, and we shall use it as a boundary condition. This is an exact relationship which must be satisfied. If as an so let us see whether our expression is satisfying this or not. As we can see from the previous slide, at DC, if we go with the expression that we have just derived, gamma in theta is equal to sigma k equal to 0 to n gamma k e raised to minus j 2 k theta, then at DC this is simply equal to gamma k. Okay. And if we do this summation, we will find that this is not equal to this expression, and something is wrong. Is something wrong with our theory? The reason this is happening is because of this small single reflection approximation that we have done, and because of that, if we had a complete closed form expression, then this anomaly wouldn't have happened. But this is happening because of the single reflection expression that we have considered. So, we will not change our concept on single reflection theory, but we will modify the expression for these gamma k's. What I mean is, the gamma k that we have so far used, the expression for gamma k is like this. Now, this we can approximate as like this, again, if the mismatch between every consecutive stage, that is zk and zk plus 1 is not too much, then we can do this approximation. And this can further be simplified like this. We use the first term of the logarithmic series. Ln here represents the logarithmic series, and from this so if I just add this up, this comes out to ln zk plus 1 upon zk. So it is a mathematical manipulation, but then since we see from experiments that when there is a small mismatch, our gamma k indeed can be approximated by this relationship, we shall take it in order to get a self-consistent solution. That is, the solution should be valid at DC. Now, if we use this expression for gamma k, and then if we go back to our expression for gamma in, if we can go back to the slides. So this becomes the product. The summation for the logarithmic series will convert to a product, and this is equal to half. The terms will cancel out each other if we take this product, and we will be left with simply ln zl upon z0, which is again approximately equal to this expression, which is equal to gamma L. So now we have obtained a self-consistent solution. So in summary, we see two things from this module, what we have discussed. First is the concept of single reflection at various junctions, that is, only the incident waves get reflected, not the reflected waves themselves will not again get reflected. And the second, so based on this single reflection theory, we obtained a very simple expression for the input reflection coefficient of a cascade of n transmission line stages. Then while doing the solution, while finding out the expression for gamma in theta, we had to do a small mathematical manipulation on the value of gamma k's. Instead of taking just the bilinear transform of z, we had to do a logarithmic approximation of the gamma k's. And with this, the reason we had to do this is to obtain a self-consistent solution for gamma k's. And then with this, we now obtain a complete expression for gamma in theta. But our design process is not yet done. We have just found out an expression for gamma in theta when we have n sections with characteristic impedance Z1, Z2, Zk and Zn. But our main problem is the reverse. That is, given a certain reflection coefficient, how can we find out the Z1, Z2, Z3 and Zk? So that is the basic problem of our design, and the way to do it, what we usually follow is to have some prototype functions, and based on these mathematical prototype functions, we will be comparing those functions with our expression that we have just derived and equating the two so that we can satisfy the values of the Zk's from the prototype function. So that is something we will cover in the next module. Thank you.